We live inside the Milky Way, yet some of its most basic facts have remained surprisingly hard to pin down. Even things as simple as whether our spiral structure has 2 arms or 4, or how many stars it contains. Estimates can swing from 100 billion to 400 billion. And here's the twist. When the Gaia Space Telescope finished its long survey, it helped reveal something even stranger. Signs that the Milky Way may not be just one galaxy, but a system that has swallowed others, leaving behind stars moving the wrong way, like footprints from an ancient collision. Now, zoom out. A century ago, many of the smartest observers on Earth looked at distant spiral nebulae and felt confident. Those were just gas clouds inside our galaxy. They were staring at entire galaxies, and they couldn't see it yet. So why did it take so long to understand something that was right in front of us? Tonight, we're going to trace the slow, beautiful chain of reasons. How we mistook the universe's biggest cities of stars for local fog. Before we can understand how galaxies were misunderstood, we need to be clear about one thing: what a galaxy actually is. A galaxy isn't just a collection of stars. It's a system: stars, planets, gas, and dust. And a far larger amount of something we can't see at all: dark matter. All of it held together by gravity, moving as a single structure through space. Our home, the Milky Way, is one of these systems. A barred spiral galaxy, stretching roughly 80 to 90,000 light-years across. At its center sits Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. That sounds precise. But here's the problem. We don't see the Milky Way from the outside. We live inside it. Our solar system sits embedded in the galaxy's disk, surrounded by stars, gas, and thick lanes of dust. That dust absorbs visible light. It blocks our view across the galaxy's plane. Large regions of the sky become what astronomers call the zone of avoidance, areas where entire structures are hidden from sight. Trying to map the Milky Way from our position is like standing deep inside a forest and attempting to draw a map of the entire landscape. You can see nearby trees. You can follow a few paths. But the overall shape, where the forest begins, where it ends, remains uncertain. The closer something is, the harder it can be to see its true form. This is why the Milky Way remained so difficult to understand for so long. Not because it's unusual, but because we are trapped inside its geometry. Ironically, that makes it one of the hardest galaxies to study, especially for its own inhabitants. Distances become uncertain. Structures overlap along our line of sight. Motion is difficult to interpret without long-term measurements. And if our own galaxy is this challenging to piece together, then the faint, blurry objects beyond it were even harder to place. Those distant smudges in early telescopes didn't come with labels. They didn't announce their distance. They didn't reveal whether they were nearby clouds or something far larger. Understanding the Milky Way was never just about learning our address in space. It was about realizing how limited our perspective really is. And if our own galaxy was this difficult to understand, the faint objects beyond it were almost impossible to place in context. Long before telescopes existed, the Milky Way was already a mystery. To ancient observers, it appeared as a faint, glowing band stretching across the night sky. It didn't flicker like clouds. It didn't move with the planets. But no one could agree on what it actually was. Aristotle believed the Milky Way was a phenomenon of Earth's atmosphere. a kind of luminous vapor ignited high above the ground. It was a reasonable explanation at the time. The heavens were thought to be perfect and unchanging. Anything diffuse or irregular was easier to assign to the air below. But even then, doubts began to surface. Some scholars noticed that the Milky Way held its position night after night. It rotated with the stars, not with the weather. It behaved like something distant, not something happening nearby. Across the Islamic Golden Age and into medieval Europe, a different idea slowly emerged. The Milky Way was not a cloud at all. It was made of countless stars, packed so tightly and so far away that their light blended together. This view lacked proof, but it had something else: consistency. Then, in 1610, everything changed. When Galileo Galilei turned one of the first telescopes toward the Milky Way, the soft glow shattered into detail. The band resolved into innumerable individual stars. What once looked smooth and misty was suddenly granular and deep. The Milky Way was no longer mysterious in the same way. It was clearly astronomical, distant, and vast. But the clarity was incomplete. Galileo's telescope explained the Milky Way, and only the Milky Way. Beyond it, astronomers were beginning to notice other faint patches of light. Small, cloudy shapes. Some elongated, some strangely symmetrical. A few even appeared to have a spiral form. These objects did not resolve into stars the way the Milky Way had. Even through improving instruments, they remained stubbornly diffuse. They didn't fit neatly into the new picture. Were they distant star systems like the Milky Way, or something else entirely? At the time, there was no reliable way to tell. Distance could not be measured accurately. Brightness alone was misleading. Shape suggested structure, but structure did not guarantee scale. So astronomy found itself in a strange position. For the first time, it had a solid explanation for the Milky Way, and no explanation at all for what lay beyond it. Even when we were right, we were only right about part of the picture. Galileo had opened the door, but he hadn't stepped through it. And beyond the Milky Way, astronomers were seeing something they couldn't quite explain. As telescopes improved, astronomers began to notice something strange beyond the Milky Way. Scattered across the sky were faint, cloudy patches of light. They were dim, diffuse, and stubbornly unresolved. Some of them weren't round. They had shape. Long exposures revealed delicate curves, winding patterns that seemed to coil around a central glow. They became known as spiral nebulae. At the time, the name made sense. Through the telescopes available then, these objects refused to break apart into individual stars. No matter how carefully astronomers observed them, the light remained smooth and misty. Without sharper instruments, there was no clear reason to think they were anything other than clouds of gas. There was also a deeper problem. No reliable way existed to measure their distance. Brightness alone couldn't help. A nearby cloud could look just as faint as a distant structure. Without a cosmic ruler, size was guesswork. So the simplest explanation prevailed. Spiral nebulae were placed inside the Milky Way, smaller structures floating within a much larger galaxy. And yet, not everyone was fully convinced. Some spiral arms appeared remarkably symmetrical, too organized to be random turbulence. A few contained tiny points of light that looked suspiciously like stars. They looked too structured to be random clouds. But suspicion is not evidence. There was no measurement that could settle the argument, no observation that could definitively place these objects beyond the Milky Way. So the hypothesis that spiral nebulae were gas clouds inside the Milky Way remained intact. Not because it was proven, but because it couldn't be disproven. The problem wasn't what these objects looked like. It was that no one knew how far away they were. And until that question could be answered, the fog remained. If you're still here with us, thank you. We truly appreciate you taking this time to explore the universe together. We hope this video has given you something valuable. Not just information, but a clearer way of seeing how vast and fascinating the cosmos really is. We're always listening, always learning, and always trying to make these journeys deeper and more meaningful for you. If you'd like to support what we do, a simple like, a subscription, or sharing this video helps more than you might think. And without keeping you waiting any longer, let's continue our journey into what comes next. By 1920, astronomy had reached a breaking point. For decades, observations had been piling up. Telescopes were improving. Photographic plates were revealing more detail. Yet the overall picture of the universe refused to settle. Two very different visions were competing for acceptance. On one side stood Harlow Shapley. He argued that the Milky Way was enormous, far larger than previously believed, so large in fact that it could contain all known objects within it. In his view, spiral nebulae were simply smaller structures embedded inside our galaxy. On the other side was Haber Curtis. He believed the opposite. Spiral nebulae, he argued, were not clouds at all. They were island universes, systems of stars comparable in size to the Milky Way, scattered far beyond it. Both men were working with real data. Both interpretations were grounded in observation, and yet, both were missing something essential: distance. There was no reliable way to measure how far away the spiral nebulae truly were. Without that information, size became ambiguous. A nearby object could appear faint. A distant object could appear small. Brightness alone could not break the tie. So the debate unfolded not as a clash of egos, but as a collision of incomplete pictures. In April of 1920, the two astronomers presented their cases publicly. The event would later be remembered as the Great Debate. But despite its name, it produced no clear resolution. No vote was taken. No verdict was announced. The audience did not leave with a winner. In fact, no one left that debate knowing they were wrong. Astronomy, at that moment, was stuck between two possible universes, both internally consistent, neither fully provable. The disagreement did not persist because the scientists were stubborn. It persisted because the scale of the universe itself was still unknown. Arguments alone could not settle it. Better reasoning was not enough. The problem demanded something else. What astronomy needed wasn't a better argument. It needed a better ruler. After the Great Debate, the problem was clear. Astronomers weren't arguing about shapes. They weren't arguing about theories. They were arguing about distance. No one knew whether spiral nebulae were nearby objects inside the Milky Way, or systems so distant that they lay far beyond it. Without distance, every conclusion remained fragile. Then quietly, a solution began to take shape. Some stars do something unusual. They brighten, they dim, and they repeat this pattern with remarkable regularity. These stars are called Cepheid variables. At first glance, they don't seem special, but their rhythm carries hidden information. The key discovery was simple. For Cepheid stars, the time it takes to complete one full cycle of brightening and dimming is directly linked to how luminous the star truly is. not how bright it appears from Earth, but how much light it actually produces. A slow pulse means a powerful star. A faster pulse means a weaker one. Once that relationship was understood, something remarkable happened. By measuring the period of a Cephid's pulse, astronomers could determine its true brightness. And by comparing that true brightness to how faint it appeared in the sky, they could calculate its distance. No assumptions were required, no guesses about size or structure. The light itself carried the answer. Cepheid variables became cosmic rulers, standard candles, objects whose intrinsic brightness was known in advance. For the first time, distance stopped being a guess. This wasn't a new theory layered on top of old uncertainty. It was a measurement. Brightness became a message. Suddenly, the universe could be measured outward, step by step, from nearby stars to distant clusters, to the faint, unresolved spirals that had fueled decades of confusion. There was only one limitation. Cepheid variables were useful only if you could actually find them, embedded within the object you wanted to measure. If a spiral nebula contained Cepheid stars, its distance could no longer hide. And one astronomer, working with the largest telescope of his time, understood exactly what that meant. And Edwin Hubble knew exactly where to look. High above Los Angeles, on the slopes of Mount Wilson, stood the most powerful telescope of its time, the Hooker telescope, a 100-inch mirror unmatched in scale and clarity. It was here that Edwin Hubble focused his attention on one particular spiral nebula, Andromeda. To the naked eye, Andromeda appeared as a faint smudge. Through smaller telescopes, it remained unresolved. But the Hooker telescope offered something different, enough resolving power to look for individual stars. Hubble wasn't searching for beauty. He was searching for certainty. Night after night, photographic plates accumulated light. And within the spiral structure of Andromeda, something subtle emerged. Points of light that changed. They brightened, they dimmed, they repeated the cycle. Cepheid variables. This was the crucial detail the great debate had been missing. Hubble measured their periods carefully. Slow pulses, predictable rhythms. From those rhythms, he calculated their true brightness. And from their faint appearance on Earth, he calculated their distance. The numbers left no room for interpretation. Andromeda was far beyond the Milky Way. Not near its edge, not embedded in its outer regions, but separated by a distance that dwarfed the galaxy itself. At the time, the Milky Way was estimated to span tens of thousands of light years. Andromeda lay hundreds of thousands of light years away, far outside any reasonable boundary of our galaxy. There was no clever argument that could rescue the old model. If Cepheid stars existed inside Andromeda, and their measured distance exceeded the size of the Milky Way, then Andromeda could not be part of it. The conclusion was unavoidable. Andromeda was another galaxy. And if Andromeda was a galaxy, then the spiral nebulae scattered across the sky were not clouds of gas at all. They were galaxies, each one a vast system of stars, comparable to our own. In a single stroke, the universe changed. The Milky Way lost its role as the entire cosmos. It became one galaxy among many. The universe didn't just get bigger, it got multiplied. This realization did not arrive with philosophical reflection or poetic language. It arrived through measurement. Numbers on photographic plates, periods counted, distances calculated. There was no need to persuade. The data spoke for itself. Andromeda was not nearby. It was another galaxy. Once that truth settled in, Everything that came before had to be re-examined. The great debate had an answer at last, not delivered from a podium, but revealed by light that had been traveling for hundreds of thousands of years. And with that answer came consequences. If one spiral nebula was a galaxy, then the sky was filled with them. If the sky was filled with galaxies, then the universe was far larger than anyone had imagined only a decade earlier. The Milky Way was no longer the container of everything. It was part of something vastly more expansive. Hubble's result didn't instantly rewrite astronomy. It should have. The numbers were clear, the measurements were solid. But acceptance did not arrive at the same speed as discovery. At first, many astronomers hesitated. They questioned the Cepheids themselves. Were these stars truly reliable? Was the relationship between their period and brightness calibrated correctly? Could dust or observational bias be skewing the results? These were not unreasonable doubts. The conclusion was enormous. It demanded extraordinary confidence. And so the resistance began quietly, not as denial, but as caution. But the data did not remain isolated. Cepheid variables were soon identified in other spiral nebulae. Again and again, the same pattern appeared, the same cycles, the same distances, far beyond the boundaries of the Milky Way. Each new detection made the old explanation harder to defend. Slowly, the language in journals began to shift. Textbooks were revised. Diagrams of the universe were redrawn. What had once been a single galaxy containing everything was now one structure among many. Still, the hesitation lingered. This wasn't because astronomers were stubborn. It was because the scale of the change was difficult to absorb. For centuries, the universe had been imagined as compact, vast, but finite in a familiar way. Now, in the span of a few years, that picture had expanded dramatically. Thousands of galaxies, millions perhaps, each one a system as complex as our own. That kind of shift doesn't settle instantly. It ripples. Careers had been built on older models. Observations had been interpreted through narrower assumptions. Entire ways of thinking had to be reconsidered. Acceptance lagged behind discovery. But it did come. By the late 1920s, the idea of external galaxies was no longer controversial. It was foundational. And once that foundation was laid, a new question emerged, one that could no longer be ignored. If galaxies existed everywhere, far beyond the Milky Way, they were not simply frozen in place. They were part of something larger, something dynamic. The discovery of galaxies had multiplied the universe, but it had also introduced motion, and motion demands explanation. Once we accepted other galaxies existed, the next question was unavoidable. What were they doing? After galaxies were finally recognized as separate systems, a new assumption quietly collapsed. For a long time, astronomers had treated the universe as a static stage. Galaxies were distant, numerous, but fixed. They were points on a cosmic backdrop. Then attention shifted from images to light itself. When astronomers spread the light of galaxies into spectra, they noticed something subtle but consistent. The familiar patterns, the dark absorption lines that act like fingerprints for elements, were no longer where they were expected to be. They were shifted, pulled slightly toward the red end of the spectrum. At first, this displacement seemed technical, easy to overlook, easy to misinterpret. But the pattern repeated. Galaxy after galaxy showed the same behavior. The farther away a galaxy appeared, the greater the shift. The explanation did not require equations. It required intuition. When a sound source moves away from you, its pitch drops. An ambulance siren stretches into a lower tone as it recedes. Light behaves in a similar way. As a galaxy moves away, the waves of light it emits are stretched. Their wavelengths grow longer. They slide toward red. This became known as redshift, and it carried an unavoidable implication. Most galaxies were not simply sitting in space. They were moving away from us. More than that, distance mattered. Nearby galaxies drifted slowly. Distant ones receded much faster. This was not random motion. It was orderly, systematic. The universe wasn't just bigger than we thought. It was moving. For the first time, motion entered the picture. Space itself was no longer a rigid container. It was changing, stretching, expanding. This realization quietly altered everything that followed. If galaxies were moving apart, then the universe could not have always looked this way. Rewind the motion, and the distances shrink. Run it backward far enough, and everything converges. The universe suddenly had a past, not just a collection of objects, but a history. This was the moment astronomy crossed a threshold. It stopped describing where things were and began asking how they got there. If the universe is expanding, then it must have been smaller before. Once the universe was understood to be expanding, another quiet assumption began to fall away. Galaxies were no longer seen as finished objects. They were not permanent fixtures, frozen in time. They were evolving. A galaxy is more like a city than a monument. Stars are born within it. Gas is slowly consumed. Energy flows, fades, and reshapes what remains. Over billions of years, a galaxy changes, not suddenly, but steadily. New stars ignite inside dense clouds of gas. Old stars burn through their fuel and grow dim. The balance between creation and exhaustion shifts. Even the graceful spiral arms, once thought to be solid structures, turned out to be something far more subtle. They are not rigid arms made of the same stars holding their shape forever. They behave more like patterns, waves moving through the disk. Stars drift in and out of these regions. Gas compresses as it passes through, triggering new bursts of star formation. The pattern persists, even though the material within it constantly changes. The spiral shape is not a skeleton. It is a rhythm. And sometimes that rhythm is interrupted. Galaxies do not live in isolation. They pass near one another. They tug. They distort. And occasionally, they collide. Despite the violence implied by the word, galaxy collisions are not like car crashes. The distances between stars are immense. Most stars never touch. But gravity does its work quietly. Disks stretch. Tails of stars arc outward. Gas clouds compress and collapse, igniting waves of new star formation. A collision can transform a calm spiral into a chaotic starburst, or reshape two spirals into a single, smoother system. Over time, these encounters leave marks: warped disks, elongated halos, asymmetries that refuse to settle. A galaxy's shape is not decorative. It is historical. Galaxies remember their past through their form. Every curve, every distortion, every uneven distribution of stars tells a story about what that system has experienced and what it has absorbed. As astronomers studied these motions more carefully, another discrepancy emerged. The visible matter, stars, gas, dust, was not enough. The observed speeds of stars, especially in the outer regions of galaxies, were too high. According to what could be seen, these galaxies should have been tearing themselves apart. But they weren't. Something unseen was holding them together. Whatever governed galaxy evolution was not limited to what telescopes could detect. There was an invisible influence shaping motion, stabilizing structure, and guiding long-term change. Galaxies were alive in ways that light alone could not explain. And understanding their evolution would require looking beyond what shines, toward what binds. Something unseen was holding galaxies together. As astronomers tracked the motion of stars within galaxies, a quiet inconsistency began to appear. Stars near the centers of galaxies behaved as expected. Their speeds matched the amount of visible matter pulling on them. But farther out, something strange happened. Stars near the edges of galaxies were moving too fast, much faster than they should have been. According to everything that could be seen, stars, gas, dust. Those outer stars should have drifted away. The galaxies should have been coming apart. But it wasn't. The rotation curve stayed flat. The motion remained stable. The conclusion was unavoidable. There had to be more mass than what was visible. This unseen mass did not glow. It did not emit light at any wavelength we could detect. It did not absorb light in a way that left clear fingerprints. It revealed itself only through gravity. This invisible component became known as dark matter. Dark matter does not shine. It does not clump into stars or planets. It interacts almost entirely through gravitational pull. And there's a lot of it. For every unit of ordinary matter, the kind that forms stars, planets, and people, there appear to be roughly 5 to 6 units of dark matter. Galaxies are not held together by what we see. They are held together by what we don't. Once this idea was accepted, the larger structure of the universe began to make sense. When astronomers mapped the positions of galaxies across vast distances, a pattern emerged. Galaxies were not scattered randomly through space. They gathered along immense filaments. They clustered at dense nodes. Between them stretched enormous voids, nearly empty of matter. This arrangement became known as the cosmic web. On the largest scales, the universe resembles a network, not a smooth fog of galaxies, but a structured framework. Dark matter forms the scaffolding. Galaxies light it up. Imagine a vast, invisible structure stretching across space, and along its beams and intersections, galaxies appear like decorative lights hanging from a frame you cannot see. The galaxies draw our attention, but they are only the visible tips. Most of the universe doesn't shine. Light tells us where stars are. It tells us where gas is heating or cooling, but it does not tell us where most of the mass resides. This realization carried an important consequence. If light was only revealing part of the story, then relying on visible light alone would always leave us with an incomplete picture. To understand the universe more fully, astronomers would need new ways of seeing, new kinds of observations, new senses. The invisible structure had been inferred. But to explore it, the universe would have to be observed beyond what the human eye was designed to perceive. To see more of the universe, we had to stop relying on visible light. For most of human history, astronomy relied on a single sense: sight. The kind of sight our eyes evolved for, a narrow slice of light known as the visible spectrum. Through that window, stars stood out clearly, bright, sharp, distant. But much of the universe remained hidden. As technology advanced, astronomers learned to observe the sky in different kinds of light. And with each new wavelength, the universe seemed to change. In visible light, a galaxy appears calm. Stars trace graceful spirals. Dust lanes cut dark silhouettes across glowing disks. but switch to infrared, and the picture transforms. Infrared light slips through dust that blocks visible wavelengths. Suddenly, regions once thought empty reveal dense clouds of gas. New stars ignite where darkness used to be. The same galaxy now looks active, restless, alive with ongoing creation. Then came X-rays. X-ray observations don't show stars at all. They reveal extreme environments, superheated gas, shock fronts, and violent interactions. Near the centers of galaxies, X-rays expose the surroundings of black holes feeding on infalling matter. What looked serene in visible light becomes turbulent in X-rays. Radio waves add another layer. They trace cold gas stretching across vast distances. They map enormous structures connecting galaxies together. They reveal features far too diffuse to glow in any other way. Each wavelength told a different story. Not a different universe, the same one, seen through different senses. A galaxy observed this way was no longer a static image. It became a layered system, stars shining, gas collapsing, energy flowing, matter cycling through phases invisible to the human eye. The universe changes when you change how you look at it. With enough wavelengths combined, astronomers could begin to build complete pictures, not just of where things were, but of how they behaved. Yet something was still missing. Seeing revealed structure. It revealed composition. It revealed energy. But it did not reveal motion. Images could show where stars and gas were at a single moment in time. They could not easily show how those components had moved or where they were headed. To understand the full history of galaxies, astronomers needed more than better eyes. They needed a way to track movement across the sky, to measure subtle shifts, to follow stars through time. Seeing wasn't enough. We needed to measure motion. By the time astronomers turned to Gaia, they weren't trying to take better pictures. They were trying to read history. Gaia doesn't produce dramatic images, doesn't capture glowing nebulae or cinematic spirals. Its strength lies elsewhere. Measurement. Over years of continuous observation, Gaia tracked the positions of stars with extraordinary precision. Not just where they were, but how they moved. Tiny shifts caused by parallax revealed distance. Slow drifts across the sky exposed proper motion. Subtle changes in wavelength uncovered radial velocity. Together, these measurements transformed the Milky Way from a snapshot into a time-lapse. The scale was unprecedented. Nearly 2 billion stars, trillions of individual data points, each one a clue. And within that vast data set, something unexpected emerged. Not all stars were moving the same way. Some followed the smooth rotation of the galactic disk. Others cut across it at strange angles. A few even moved against the general flow. At first glance, it looked like noise, measurement error, statistical oddities. But the pattern held. These stars were not randomly misplaced. They shared common motions, common energies, common origins. They didn't belong to the Milky Way's original structure. They were immigrants. This was the moment the galaxy stopped looking like a single, coherent system and started resembling an archive. One of the clearest signatures pointed to an ancient collision, a massive event that took place roughly 8 to 11 billion years ago. A time when the Milky Way merged with another large galaxy, now known as Gaia Enceladus. The stars from that galaxy were still here, not clustered together, not labeled, but moving. Their motions preserved the memory of the impact, long after the event itself had faded from view. Another story unfolded closer to home. The Sagittarius dwarf galaxy, smaller but persistent. has been interacting with the Milky Way for billions of years. It has passed through the galactic disk multiple times over the last 4 to 5 billion years. Each pass stretched it thinner. Each encounter stirred waves through the Milky Way's stars and gas. And it may not be finished yet. What Gaia revealed was not chaos, but consequence. The Milky Way is not a pristine structure that formed once and settled forever. It is a product of accumulation, of mergers absorbed, of systems disrupted, of stars captured and redistributed. You can rewind a galaxy by watching how its stars move. This realization reframed a long-standing mystery. We didn't misunderstand the Milky Way because we lacked intelligence. We misunderstood it because we were living inside the aftermath. We were trying to describe a system shaped by collisions while standing amid the debris. The spiral arms, the warped disk, the uneven distribution of stars, these were not flaws in observation. They were fingerprints. Milky Way wasn't just large. It wasn't just complex. It had a past. And understanding that past explained why its present had always been so difficult to interpret. But even motion has limits. Tracking stars tells us where the galaxy has been and how it was assembled. It does not fully explain what is happening right now, especially in regions hidden from view. To complete the picture, another barrier still had to be crossed. But motion alone couldn't tell the whole story. Once astronomers learned how to read galaxies properly, individual examples stopped being curiosities. They became evidence. Not every galaxy needed to be understood in full detail. Each one only had to answer a single question. Take Messier 82. M82 is not calm. It is a starburst galaxy, forming stars at a rate far beyond normal. This activity is not random. M82 sits close to a larger neighbor, Messier 81. Their gravitational interaction compresses gas inside M82, triggering waves of rapid star formation. The result is visible even from a distance. Massive outflows, superwinds, stream away from the galaxy's core, carrying gas and dust into intergalactic space. Material that might have formed future stars is being pushed outward instead. M82 shows what happens when a galaxy is disturbed. It reacts. Its structure changes. Its internal balance shifts. Star formation accelerates and then exhausts itself. Now consider a very different case. The Triangulum Galaxy, Messier 33. M33 is faint, diffuse. For a long time, it was difficult to classify. It didn't look large enough to be a major galaxy. It didn't look small enough to be a simple satellite. Only once its distance was measured accurately did its role become clear. M33 is a true spiral galaxy, a member of the local group, smaller than the Milky Way, but independent. Its example is subtle but essential. Position matters. Distance matters. Without knowing where a galaxy sits, even its identity can be misunderstood. And then there is the Sombrero Galaxy. At first glance, it appears simple. A bright bulge, a sharp dust lane, a clean, elegant shape. But surrounding that neat appearance is something unexpected. An unusually large population of globular clusters. These ancient star clusters orbit far beyond the visible disk. Tracing the galaxy's gravitational influence, their motions imply a mass far greater than what its stars alone can account for. The Sombrero Galaxy looks orderly, but it is heavy. Its shape suggests simplicity. Its dynamics tell a different story. Each of these galaxies answers a different question. M82 shows how interaction drives change. M33 shows how distance defines identity. sombrero shows how appearance can mislead. They do not contradict one another. They reinforce the same picture. Galaxies are shaped by their environment, by their history, by forces that are not always visible. Every galaxy tells a different part of the same story. And when those parts are placed together, the Milky Way no longer stands apart. It fits. Our galaxy is not strange. It is not exceptional. It is simply the example we happen to live inside. Galaxies don't contradict each other. They explain each other. Yet even with these examples, there was still one layer missing. Large galaxies evolve slowly. Their changes unfold over billions of years. To understand the engines driving that evolution more directly, astronomers turn to something smaller, more compact, more immediate. Sometimes, the fastest way to understand a galaxy is to study a much smaller engine. By this point, astronomers had learned something important. To understand galaxies, you don't always have to look farther away. Sometimes, you have to look smaller. Quasars were among the most powerful objects ever discovered. At their centers sit supermassive black holes, surrounded by vast disks of infalling matter. As material spirals inward, enormous amounts of energy are released, light, radiation, and tightly focused jets that can stretch across entire galaxies. These systems shape their surroundings on the largest scales. But quasars are distant. They evolve slowly. Their details are difficult to observe directly. That's where microquasars come in. A microquasar is a scaled-down version of the same engine. Instead of a supermassive black hole, it contains a stellar mass black hole or neutron star. Instead of a galaxy-spanning disk, it draws matter from a nearby companion star. The physics is the same. Only the scale is different. Because microquasars are much closer, astronomers can watch them in real time. Changes that take millions of years in quasars unfold over days or weeks here. One system became especially important: SS433. SS433 lies within our own galaxy. At its core is a compact object, pulling material from a companion star, forming an accretion disk and launching powerful jets of matter into space. These jets are not steady beams. They wobble. They precess. They sweep out cones as they move, leaving unmistakable signatures in both radio and X-ray observations. What makes SS433 exceptional is its energy. Particles within its jets are accelerated to nearly the speed of light. Observations have detected gamma rays with energies exceeding 10 teri-electron volts, a clear sign of extreme acceleration. This is not decorative violence. It is physics at work. By studying systems like SS433, astronomers learned how energy is transferred from compact objects into their surroundings, how jets heat nearby gas, how they stir the interstellar medium, how they regulate star formation by injecting turbulence and removing material. These processes are not confined to small systems. Scaled up, they help explain what happens in galactic centers, how active black holes influence entire galaxies, why star formation can be triggered or shut down over vast regions. The same physics scales up. The universe repeats its rules. Microquasars showed that galaxies are not shaped only by slow gravitational drift. They are influenced by engines, compact, energetic, and persistent. And most importantly, these engines are understandable, not because they are simple, but because we can observe them clearly. SS433 doesn't just explain itself. It explains how similar processes operate where we cannot watch directly. This connection between the small and the vast, closed a loop. Galaxies are not mysterious because they follow unknown laws. They are difficult because their scale hides familiar physics. Once you identify the right place to look, the complexity becomes readable. Understanding didn't come from inventing new ideas. It came from seeing the same ideas in the right context. And that realization brings us back to where this story began. Inside a galaxy we once thought we understood, but never fully saw. And all of this leads back to a simple realization. When we look back at this story, the mistake becomes easier to understand. We didn't misunderstand galaxies because we lacked intelligence, and not because early astronomers were careless or naive. We misunderstood them because of where we were standing. From inside the Milky Way, our view was limited. Dust blocked the center. Distance blurred the edges. Motion was too subtle to detect. The universe wasn't unclear, our perspective was. Each major shift in understanding came not from a new idea, but from a new way of seeing. Cepheid variables gave us distance when distance had been guesswork. Redshift showed us motion when the universe was assumed to be still. Multi-wavelength astronomy revealed hidden structure when light alone misled us. Gaia gave us movement and memory when snapshots weren't enough. Vista let us see through dust when absence had been mistaken for emptiness. None of these tools contradicted what came before them. They completed it. Understanding arrived gradually, one lens at a time, and with each lens, the universe grew more coherent, not more confusing. Galaxies stopped being decorative spirals. They became systems with histories, with collisions remembered in stellar motion, with energy flowing through gas and dust, with invisible structures shaping what we can see. The Milky Way, once the entire universe, became one example among many. Not diminished, but contextualized. This is why it took so long. Not because the truth was hidden, but because it was larger than the tools we had to uncover it. The universe did not change while we were learning. It was always doing what it does. Forming stars, merging galaxies, expanding quietly into space. What changed was us. Our instruments grew more precise. Our questions became sharper. Our assumptions loosened. And slowly, the picture aligned. Today, when we look at distant galaxies, we recognize patterns we once struggled to see in our own. We understand that complexity does not mean chaos, that motion carries memory, that structure emerges from long histories, not instant design. And we understand something else as well. We are not separate observers. We are part of a galaxy that is still moving, still changing, still shaped by events billions of years in the past. To understand galaxies is not just to map the universe. It is to locate ourselves within it. The truth didn't arrive all at once. It never does. But lens by lens, step by step, the universe became readable, not because it finally revealed itself, but because we finally learned how to see. The universe didn't hide the truth from us. We simply had to learn how to see it. If you're still here with us, thank you. We truly appreciate you taking this time to explore the universe together. We hope this video has given you something valuable. Not just information, but a clearer way of seeing how vast and fascinating the cosmos really is. We're always listening, always learning, and always trying to make these journeys deeper and more meaningful for you. If you'd like to support what we do, a simple like, a subscription, or sharing this video helps more than you might think. And without keeping you waiting any longer, let's continue our journey into what comes next.